Hello to everyone and welcome to our presentation about an automated pipeline for a browser-based city-scale mobile 4D UR application based on historical images. So how to turn historical sources into a 4D model automatically? That is our basic question/challenge. And you may know that specifically from contemporary photos, automated 3D modeling is more or less solved since the mid-2000s. So you may know about Navelli et al. 2006 as a main publication on this. So why this is challenging for historical images? You have to know that specifically scanned analog records usually have unknown camera metrics, so they do not have any metadata information natively, and you see one example on the left side, they have low radiometric and geometric resolution. Specifically for historical content, you have in addition the problem that even landmark buildings are usually shown, documented by very few historical images. And these images are often showing similar views. Consequently, on the bottom left, current state-of-the-art algorithms do not work very well. With regards to 3D viewers, there are also lots of available for mobile devices. So again, the question, why building another one? These current 3D GeoViewers are mostly only showing a contemporary state, not a historical one and not a 4D one. And they are often designed as native apps, so you have to install them first. And one thing of relevance for our purpose is that they are lacking opportunities to add user-created content. Our starting point were, at the one hand, several technologies. So for WebGL based, or you have several WebGL based frameworks, X3DEM, 3JS. Also, there are some pipelines for creating of 3D content, cultural heritage content are available. You may see for having an overview about this on the Europeana 3D Task Group publication from this year, and currently a Never tender is examining this in more detail, won by the Commission. Also, there are several viewers available for 3D cultural heritage content, 3D Hop, Hexalab, Inception, many more. With regards to photogrammetric/AI-based reconstruction from images, of course, you are having several state-of-the-art algorithms/approaches, SFM, SIFT, RIFT, DELF, and so on and so on. If you have a look on publications with regards to 4D content creation and cultural heritage, you have around 330 publications dealing with this content only from the main conferences during the last 30 years. With regards to these objectives, we have created a pipeline, and maybe it would be important to have a look on these two branches for our pipeline. One branch is to deal with historical photographs. So in the first step, to determine what are photos with corresponding object views. In the second step, to reconstruct the camera positions and the parameters. Another branch, step 3 and 4, is dealing with historical ground plots, its vectorization, and also the creation of simple 3D geometries out of these vectorized ground plots. By the way, step 3 we will not mention explicitly in our talk today. In the heart of our pipeline is an application, a 4D browser-based mobile application, which merges both branches. So these simple LOD 1.5 geometries with projected textures. This projection is taking place on the fly. And we are serving two separate or different scenarios with this. At the one hand, to enable people to have an idea about historical cities, historical places looked like over times. A second one is to enable people to co-design the future city by defining where should be loading points, charging points for e-mobility, where should be bus stops, where should be parks, and so on and so on. Both are served by the same application kernel. Let's have a look at the first step.
Okay, then let's start with step 1, how to find photos or more general images of interest. If we are crawling through large repositories, we have to deal with large amount of data, namely thousands of images or even millions. And crawling such a repository only based on metadata is typically very time-consuming, caused by misleading or even wrong metadata. Therefore, this crawling process is mainly handcrafted until now, and our goal here is to support at least or even automate this image search. Our vision there is that we have a query image that contains our object of interest, which is maybe some special building. And in the second step, we perform an automated comparison against other images. And these other images are called reference images. And we get back a result list that is ordered by relevance of the query image referring the reference images. That means the most relevant image appears at the top, and the most relevant images appear at the top, and the less relevant images appear at the bottom. And this task can be solved by mainly two different approaches from the area of computer vision, which is image retrieval and image classification. In the following, I will limit myself to the image retrieval approach, and the most important question for that is how to represent an image, or more precisely, its typical and its characterizing features by so-called appropriate descriptors. And there are different approaches around. The more common approaches in computer vision are SIFT, FLAT, and all that stuff. And during the last years, there came also up alternative approaches that are based on so-called convolutional neural networks. And these networks, these convolutional neural networks, are able to deal with image data especially. And in a contribution in 2016, Lazariv showed that a CNN-based approach outperformed the standard approaches here that are common in computer vision as SIFT and VLAD and so on, that this CNN-based approach is beneficial in comparison to the standard approaches. And in this paper, they used the Oxford dataset. And this dataset is interesting in the sense that it contains photos of historical buildings. And this is, at least to some extent, comparable to our data. We have somehow different data, not exactly the same data, but it is really good comparable, and therefore it makes sense to show into this direction. And we decided to follow this approach from Lazariv while implementing our image retrieval here. And the basic idea is to use convolutional neural networks to find these local descriptors that are characterizing the object or the image of interest. And such a CNN, if you're not familiar with that, just imagine this as a sequence of filters, and these filters are extracting the descriptive characteristics of an image, such as edges and shapes, and you get out of this at the very end a vector simply. More precisely, it is a tensor, and you can see here such a convolutional neural network, which is especially the VGG16, which is also quite common in machine learning. And we used this network that is pre-trained. That means we know already the weights. The weights are trained, learned already, and we are using this common structure of a CNN. And we push in an image, and you can see here these rectangles are the different filters. And at a special point that we can choose, And we decided to go for this point here, according to Rasafian. We decided to extract then this vector that comes out of here. More precisely, this is a tensor, but for simplification, just think of a vector. And therewith, we can characterize the image and its characteristics. And what we have at the very end is the vectors for a vector for every single image, and then we can compare or we can measure the distance between the images on the basis of these vectors. That means we got simply distances between images as a kind of measure for this resulting rank list, and then we can order based on these measure or based on this distance measure. So how does it look like? Here we have such a retrieval. We have a query image, we put it into our retrieval pipeline, and we get back this result list. And here we have at the top left the most relevant image, which has the smallest distance to our query image. And following this result list from left to right and from top to bottom, the distance is increasing, and we got more and more less relevant images down the list. So what is the main result of this? We saw image retrieval based on CNN works basically, and especially for historical images. This is the good news. We also had no problem with the heterogeneity of images. We have photography, we have painting, we have color, we have grayscale. There is a lot different types of images in our data sets typically, and the approach based on the CNN is able to deal with that. In that sense, it is quite nice. Nevertheless, the quality of results depends on the type of object we are retrieving for. It works better for landmark objects. It is not so good for non-landmark objects, but this isn't really a surprise. We performed our experiments referring a fixed set of images, referring reference images, and the results there can be improved probably if we combine this with a metadata search, and this then acts as a pre-filtering. The bottom line, nevertheless, is image retrieval can assist the researcher to semi-automate the image crawling process, and hopefully this will be a strong support and will also save time for the researcher in order to find images, objects of interest. What are our next steps, especially for this image retrieval here? We want to identify quite clearly what are the success drivers, and we will try to further improve our results, and also improving computational efficiency will be an issue at the moment. Retrieving for a single image against within roughly 1,000 images for reference takes between 10 and 30 seconds. And this still can be improved. Nevertheless, computational efficiency was not our main issue so far, but there we will work further. Okay, that's it so far for step 1.
Now let's switch to the second step, the reconstruction of camera positions and parameters. So the question is how to find orientation of historical images. So as mentioned before, state-of-the-art tools for contemporary photos do not work well with historical ones. So in our case, we are using a combination of Rift with a matching of quadrilaterals as a feature-based approach. Let's maybe a look on the pipeline, and you see that there are several filter options also included here. I will not focus on this very much, but we can talk about this later. So now let's switch to a fourth step. This is the model generation and our 4D browser-based application. So this application is based on Three.js, and also dealing with MySQL plus a Apache for metadata/data handling. Some key features is it's both mobile browser capable plus also capable to deal with desktop browsers. The heart of this application is the dynamic 4D object creation from building footprints plus the projected image textures on the fly in the application browser. Also, of course, we are having a 4D time slider. You do not see it in the video, but what you can see in the video is that people are enabled to co-design with textual information, so they could add their points of interest and type in what might happen there at a specific time. We tested this application for several times, so according to Krug, with thinking aloud methods, also with a small sample of 5 persons only and some given tasks, so to retrieve information from POI, for instance, or to gather information about a given object. So most tasks or all tasks could be completed by all participants, but some interesting findings were for us that nearly all subjects are used the application in a portrait mode, that means in an upright position. And we were faced with several usability challenges, not surprisingly, but one thing of interest for us was that it is not clear if you have a sensor-based application which interacts with the orientation of your device, that this is not intuitive for all users, so we had to use include a video showing this in advance. What's next steps? So concerning UX, of course, we have to optimize, or we currently doing the optimization of the UX. Also, it's very much about the data retrieval from image repositories. And another thing is optimization for algorithms for texture projection, plus also frustum-based filtering. With regards to the modeling pipeline, it's the vectorization of ground plots from historical images, plus also another task is to combine the 3D reconstructions and testing and optimizing this pipeline. Many thanks for your attention. We are looking forward to discuss with you now.